We will now take a look at the Python example for a linear layer. So for a linear layer, the shape of the input and the output tensors are given here. So we have an input, given the shape is n star h in, where star means any number of additional dimensions and h in means the in features like we've seen before. The output has the shape n star and h out, where all but the last dimensions are the same shape as the input and h out is the out features like we've seen before. Capital N is a batch size. Star is usually the index for the test set. H in is the length of our input signal, and H out is the number of classes or detectors that we desire. The edge index is for different sets of training and data. Optimization is performed one batch after the other. This saves memory because only one batch is loaded in memory. In our example, let's imagine that we have two input signals that we want to detect, one increasing and one decreasing. So we have here x0 is given by 1 and 2, and x1 is given by 2 and 1. We will assemble these two signals into a two-dimensional tensor, some matrix, where each signal is one row. So now we have this matrix called x, and here we have the x0, 1 and 2. Here we have x1, 2 and 1. We want to have two detectors, one for the first signal and one for the second signal. The desired output of the first detector should be 1 for the first signal x0 and 0 for the second x1. On the other hand, the second detector should output 0 for the first signal x0 and 1 for the second signal x1. The desired output is also called target in deep learning, machine learning, neural networks nomenclature. We assemble the desired outputs for targets in a matrix where each detector corresponds to one row. So here we have the first detector. Like we've said before, it should be 1 and 0 for the first signal and 0 and 1 for the second x1 signal. For our linear layer, we now need to find the weights or the coefficients of the matrix A and bias B such that the desired output Y is approximated given out the training set X. So we have that this matrix should be our input matrix X multiplied by A transpose plus B. This is a matrix of coefficients or weights. This is the bias. And in this simple case, we can actually find a closed form solution. So if bias is 0 and 0, and the A transpose is the inverted X times Y, then we have a closed form solution for this problem. If now we have more samples in our training set for X and Y, we will get tall matrices. For instance, we could add another input x2, for example, 1 and 1. For each, both outputs should be 0 as target. For the non-quadratic matrices, we can compute the pseudo-inverse, which minimizes the mean squared error between the network output and the desired output. And it's given here in these equations. Observe that this does not include the bias array B, which might lead to better approximation and also needs the mean squared error. Depending on the application, we might want to use a different error measure, also called loss function. A simple and widely used loss function is the mentioned mean squared error loss. So pytorch has this function implemented, as a mean squared error loss. And for detectors of different classes, usually the so-called cross entropy loss is used. And it creates a distance or divergence function between two probability distributions. Here, the probability distributions are the target distribution, probability 1 for the true class and probability 0 for the false class, and the distribution that the neural network generates, a predicted probability for each class with high probability value for the class that the network thinks is at its input. In PyTorch, we have also this cross entropy loss, and you also find all the details in PyTorch documentation. To obtain a better solution and include other loss functions, in general, numerical optimization is used to find the weights of coefficients which minimizes a given loss function. Observe that the loss function produces a single number or value for a given training set and given weights. The weights are then updated during the optimization to reduce the loss function. Common optimizers are, for example, the stochastic gradient descent, SGD, and adaptive moments, ADAM. After we obtain the weights from the optimization, we have to see if it generalizes to other examples or just works on the training set. For this, we have the validation set containing new input and target samples. This is used to modify the neural network structure until it performs on new samples or examples sufficiently. Once we have a good neural network structure, we test it on the test set, another set with new samples or examples to test the performance.